Welcome to this third part of the lecture on point cloud registration and looking into the ICP algorithm. And today we want to look into the most general, let's say, nonlinear least squares approach to point cloud registration. So far we have discussed finding point cloud registrations given known data associations, where we looked into finding the optimal transformation to transform the two point clouds on top of each other. And then in the second part of the lecture, we looked into the question, what happens if we don't know the data association and go for the ICP-based approach, where we find the closest point in another point cloud in order to estimate correspondences. In the third lecture here today, we want to look into a least squares approach where we don't use this SVD-based registration, but look in a somewhat more general formulation of that, which in the end leads to a Gauss Newton-based iterative alignment, and see what we can do with this for point cloud registration. So what we have seen in the previous lecture, we had this example here of those two bunnies, and the goal is to align those bunnies. So for every point in point cloud number 1, we look for the closest corresponding partner in point cloud number 2 based on a nearest neighbor criterion. So we look for the closest point and then say this is a correspondency, and then try to minimize the distances between those two point clouds and actually minimizing a squared distance. And if you run this video, we see different iterations which are ongoing here, which try to find a data association, then perform the alignment step, then again look for data association, do the alignment step, and so on and so forth, until after a couple of iterations, those two point clouds are aligned with each other. So, and we started out originally with a very simple form of this alignment. So consider we have two point sets, y and x over here, in some different coordinate systems. One could be a global coordinate system, which is available in some form of map form. This could be your local sensor frame. It could also be two different sensor frames. That doesn't really matter. And then we have the correspondences over here, indicated as a set C, which are these gray lines, knowing this point, and these points, they should correspond, and those 2 points should correspond. And initially we assumed this to be known. Then in the second part of the lecture, we relaxed this assumption and tried to estimate this C. And then based on this information, we can estimate the parameters of a rigid body transformation, so a rotation matrix R and a translation vector T, to perform the point set Xn into a point set Xn with a bar on top of here, which then should be in the coordinate system of the point set Y. And this should happen under the constraint that the sum of differences between the point cloud, the red one, and the transformed one should be minimized. And then we could apply that transformation and transform the points, the blue points, onto the red ones, and assuming that there's some noise in this process, there may be small variations in there, but overall we should get the alignment that minimizes this squared error. So we are minimizing this error function over here, which is the distance between the point sets in the target set, so the red ones, minus those transformed blue ones, and then trying to find the best transformation so that this error is actually minimized. And that's a least squares approach. And we used an SVD-based technique in order to find this transformation. And in the lecture today, we will not use this SVD-based formulation, but use a general least squares approach. And this has the advantage that we can take different error functions into account and not just these simple ones. We also have different ways for dealing with uncertainties of these points, and different advantages why in some situations we may want to go for the least squares approach and leave the SVD-based alignment. If SVD-based alignment works well for you, it's compatible with your error function, you can do everything you want to do, there's no reason to go to these least squares, to this least squares approach. You can do the same with your SVD-based technique. If you, however, want to add additional information into your error functions, maybe in the end want to go to a non-rigid alignment of point clouds, if you know that this object can be deformed, then you also need to go towards a least squares solution, like the one we are shown over here. Okay, so the goal, again, is to find the parameters of a transformation that best aligns my data points. And we looked into different parts of the lecture. In part number 1, we looked into known data association. In part number 2, we said we want to estimate the data association leading to the ICP approach. And then in the lecture today, we want to look into the least squares or robust least squares approach. So in the first part of the lecture, known data association, and here we could derive an efficient, computable, optimal, and direct solution for finding the rigid body transformation. So everything perfect in this setup, nothing to do here. So if you know your data association, part 1 is sufficient, you don't need to know more. Typically, we, however, don't know the data association, so then part 2 becomes interesting for you, and then there is no direct or optimal solution available, and we need to basically estimate or guess correspondences and then end up with an iterative approach in order to align those point clouds. We can also illustrate this, the ICP approach. So we typically have our point set. We look for points, either sampling them from a mesh or selecting points based on a laser range scanner, for example, which generates 3 data points. Then we look for corresponding partners in the other point set, typically the closest point with the smallest Euclidean distance, for example. And then we use this information in order to minimize the distances, so transform one mesh onto the other or one point cloud onto the other. And then we are iterating this process of finding new correspondences given this improved initial guess and iterate this procedure until convergence. And we also looked into different variants over here. Should we take into account all points for this alignment or just a subset? How do we find the data association or a good data association? So we looked into a point-to-point metric, also point-to-plane, other techniques in order to try to find compatible point sets for the alignment. We can weigh our correspondences and also looked a little bit into outlier rejection. What happens if a certain number of points are caused by outliers, for example, when operating in dynamic environments, and we generated solution for that, which are kind of variants of the ICP algorithm. So for finding those correspondences, there are different ways on how to do this. And again, finding a good data association is key. And we had some kind of, let's say, best practices. So investing in your data association is key. If your data association is wrong, you're not getting the correct alignment. So putting a lot of brain power and finding good data associations is key. And this still holds for this part of the lecture. Nothing changes in here. If you have an initial guess, for example, from wheel odometry or from other sensing modalities, you should exploit that information because a good initial guess helps you to do better data associations and in this way end up with a better alignment. We also have seen that normal-based metrics typically work better. So if you, for example, use the point-to-plane metric, it typically works better than the point-to-point metric. We will see something similar here today, and we need to take care of outliers, especially in dynamic environments. And today we want to look into the point cloud registration using a nonlinear least squares approach. So basically going into the standard least square error minimization and not exploiting kind of the special properties that we did for the SVD-based alignment in the first part of that lecture, but going to a general approach. And again, you may ask yourself, why should I care? Why do I need a nonlinear least squares approach to do this? And there may be multiple reasons. So the SVD solution basically assumes point-to-point correspondences. And maybe you have different ways for defining your correspondences. You have more complex error functions, so to say, which then require a more general formulation because you can't put that into the SVD-based alignment. Also, the least squares approach, at least if you have Gaussian uncertainties in your measurement noise, is a statistically optimal solution. So you can better take into account uncertainties. If you know that points have certain, let's say, more complex shapes than just a single weight for your correspondency, but you have more complex shapes of your alignment, you may take that into account in the least squares approach. Those information is often hard to get, but if you have it, you could exploit it better in a setup here. And what you do then is you run typically a Gauss Newton or Levenberg-Marquardt approach. Typically here we use Gauss Newton and perform an iterative error minimization in order to come up with a solution. And you want to do that as a starting point using the 2D point-to-point ICP. So something we can perfectly solve with the SVD-based approach, but as an illustration, show you how we can do this, and then in the second step, generalize this to the point-to-plane metric, for example. Okay, so let's start with the least squares approach for 2D point-to-point registration. So we have point sets in 2D, not in 3D. This makes a lot of the computations easier, and then we want to find the rigid body transformation consisting of a 2D shift vector, or translation vector, and 1D rotation matrix in order to align those point sets, so in the 2D plane. Okay, so very similar to before, we want to minimize the Euclidean distance between the points after the alignment. We have an error vector which tells us the discrepancy for one point correspondency, so what's the distance between the transform point and the actual point where it should be. We can put our transformation parameters in here of our rigid body transformation, rotation matrix R and translation vector T. Here in this example, this is now a 2D vector, and this is a 2x2 matrix, a rotation matrix, so that the parameters for the transformation are called Tx, Ty, and theta, which is the translation X, translation Y, and the rotation in order to find the alignment. So explicitly, this is the error vector we are going to minimize. And the question is, how do we perform this error minimization? And that's kind of the standard approach. You take your error vector, if it's nonlinear, and this is the case here, because it's a rotation matrix. So in this matrix R, there are sine and cosine functions in there. Therefore, this is a nonlinear error function. We need to linearize it. So compute a linear approximation of the original problem. And then work with this linearized function. We basically compute the first derivatives, set it to 0, solve the remaining system of linear equations, which then provides us with a solution to the problem, iterating this, of course. And so in order to do the next step, in order to linearize our error function, our nonlinear error function, we need to compute the Jacobian of this function. So we need to take this error function here into account and compute the Jacobian. That means we are taking this error function E and need to derive it with respect to the three parameters. So we take this error function E, we derive it with respect to Tx, we derive it with respect to Ty, and we derive it with respect to theta. And that's what we're going to do, which leads us the Jacobian. In this case, this is a 2x3 matrix exactly. We have a two-dimensional error function because we have the function has an x and y component, and it has three parameters, so we have a 2x3 Jacobian. Again, the Jacobian, to be written in this form, consists of the partial derivatives of my error function with respect to the individual parameters. So here we have kind of the x dimension of the error function, the y dimension of the error function, it's a two-dimensional error function, and derived with respect to the three parameters, so which gives us these 6 elements that we need to compute in order to formulate the Jacobian. And this Jacobian is then the common component that I need in order to generate a linearized error function. And then I'm just following the standard least squares procedure. I'm just using this Jacobian E in order to formulate the system of normal equations, and then solve this system and come up with a better estimate of my parameters Tx, Ty, and theta. Okay, so how does it look like? We need to compute those partial derivatives. That's the next thing that we need to do. So we take our error function into account and need to now derive this error function with respect to Tx, with respect to Ty, and with respect to theta. Okay, so we look into this error function here. We need to derive it, for example, with respect to Tx. So Tx, the translation vector in x, only pops up here in the first dimension of this translation vector. This part is independent from Tx, this is independent from Tx. This is a linear term, so if I derive Tx with respect to Tx, I get out a 1. This is exactly what we're getting here, a 1 over here. If we take the first dimension of this function and derive it with respect to Ty, Ty never pops up because this is the second dimension, this is the third dimension, it's not in here, it's not in here, it's not in there, so this gives me actually a value of 0. And the same holds for the second dimension of this function. If I derive it with respect to Tx, I get a 0 in here, and Ty a 1. So these components, the first 4, are just zeros and ones. So everything is linear in here. There is no nonlinearity. You can directly see this because we just have this two-dimensional vector here, which has Tx and Ty as linear elements in there. There's no whatever quadratic function or other non-linear form. The only nonlinearity that we have is actually this rotation matrix over here. So this is a rotation matrix. That means it contains sine and cosine functions, depending on the parameter theta over here, and we need to derive it with respect to theta, so those in those elements, the theta doesn't pop up, so this is the only thing which remains. So what we basically need to do, we need to compute the first derivative of that rotation matrix with respect to theta, because this value here is independent from theta. This is then just a constant factor. So we can write it in short form. The 2 by 2 matrix here is the identity, and then we have the first derivative of the rotation matrix with respect to theta multiplied with the vector xn, which then gives these missing two components. Why do these components look like that? You can see this very easily if you compute the first derivative of your rotation matrix. So you take your rotation matrix, this is a standard 2D rotation matrix describing rotation around theta, and you compute the first derivative with respect to 0. That means we compute the partial derivatives of those 4 entries. So the first derivative of cosine theta with respect to theta gives us minus sine of theta. That means this cosine theta turns into minus sine of theta, and the sine turns into the cosine, which you can see over here, and then this is the first derivative of our rotation matrix with respect to theta. So I'm just taking this matrix and multiplying it with xn, a 2 by 2 vector, which is the point coordinates of my original point set, and then this gives me this vector over here consisting of these elements. So this xn written in this form and yn are the x and y coordinates of this vector xn. So these are the original coordinates of my points. And so this is my Jacobian. This is the elements that I need to compute. And with this Jacobian and the individual error vectors over here, I can now formulate my least squares problem. So what do I need to do for this? I need to compute my normal equation matrix, which takes into account the Jacobian in order to set it up. I need to compute the right-hand side of my coordinate system, taking into account the Jacobian as well as the error vector evaluated in a position. And then I need to solve my resulting linear system. So these are the steps that I need to do. And then I can just follow the standard least squares procedure. So this is my Jacobian. As a result of the Jacobian, I can compute my matrix H, n, which is the Jacobian transpose times the Jacobian, holding only for the point correspondence n. I can do the same for the right-hand side, bn. So the vector of the right-hand side is J transposed times E, the error vector for n, and then I need to sum over all correspondences. So my matrix H is a sum over this matrices Hn, and same for the right-hand side. So my matrix H is this form, vector B has this form, and then I have all the components that I have, and I need to solve H times delta x, so the update in the parameters. So this vector x is now here the parameters of my transformation, so tx, ty, t theta, tx, ty, theta, and basically the increments of that. And so I need to solve this system, which I can in this form very easily solve by just inverting this matrix. This is a 3 by 3 matrix, remember. H is a 3 by 3 matrix, and I can easily invert a 3 by 3 matrix. So this is an easy way, just inverting the matrix and getting my update of my parameters. So I update my transformation parameters, and I iterate until convergence. So the standard least squares approach. So what I've replaced in here is basically the SVD-based alignment that I used in the first part of the lecture, we derived in the first part of the lecture, by the standard least squares approach. And the advantage is that I can take more complex error functions here into account, which then will lead to different Jacobians, of course. So I need to always compute my Jacobian by hand, and depending on the internal representation that I'm using, my Jacobian will change as well. But it allows me to do a more general alignment. So let's see how that looks like. So this is the example that we already used in the previous part of the lecture, the 2 points that should be aligned, the blue one and the orange one. We are looking for closest points. So we're going over all those points in the blue set, trying to find a correspondency in my kind of reference scan to which I want to align it to. So this would be the yn, this would be the xn over here. And then I'm estimating my correspondencies just based on the nearest neighbor assumption over here, and I compute the alignment after the first step of the least squares approach. I'm actually ending up being here in this configuration, and then I'm basically repeating this process again. I'm re-estimating my correspondencies, how the new correspondencies look like. I compute my alignment, and in every step you can see some of the correspondences will change, and we very slowly go a step forward until the 2 point clouds are finally aligned. So in this case over here you can see both point clouds overlap perfectly, so we have found the transformations which align the original point set with our target point set. And we can actually plot the error over time, so these are the iterations, this is the error, and we can see how the error basically goes down in something like after, in this example, whatever, 15, 16 iterations, something like this, we actually lead to the situation where nothing changes anymore and the system has converged. This was a simple 2D example, something that we could have solved as well with the SVD-based approach. There was no need for going to the least squares approach in this example over here, but just as an exercise, we started with this. In the next part of the lecture, we want to do the same thing with the point-to-plane distance or point-to-plane metric. So leaving these point-to-point data association, but going into point-to-plane. Just as a reminder, point-to-point metric was taking the different point sets and basically finding the closest points and trying to minimize these distances. What the point-to-plane metric does, it basically takes those distances and projects them on the normal vector of the individual, of the normals that are generated from those points or from those surfaces, and then only computes the projected error. So we also had this other plot which looked like this. So for every point in my point cloud here, I'm looking for the corresponding partners, and then can estimate the normal and basically project the error onto the normal, and then not taking this distance, but taking this distance into account. And this is basically the same as using the normal vector that I'm computing and multiplying it with the error vector that I had for my point-to-point alignment. So with this dot product, I'm basically projecting my error vector E onto the normal vector and then compute the sum of squared distances over this function. Okay, so what we need to do, we need to compute normals, and we can compute normals in a point cloud typically by just iterating over the neighbors. So for every point, we look to its neighbors and then compute here a normal vector, and that's basically what you see here. A simple estimation of the normals. You can do also more advanced techniques. You can compute basically, take the points in the local neighborhood into account and look for the eigenvectors and eigenvalues that are generated by those points, and then take the eigenvector that corresponds to the smallest eigenvalue. So this is basically the normal of the surface, and then you can actually get this normal information. Or you, depending on the noise that you have, you just take the cross product. So there are different ways how you can do this in an either very efficient way or in a slower and more accurate and more robust way. Whatever way you do it, you just need one way for computing this normal information. Okay, so then we said our objective function should be the sum over the error vectors multiplied with my normal vector. So if I expand it, this will now be my error function or my objective function that I aim at minimizing. So what do I need to do? I need to compute again the Jacobian of this error term. So this is now my error function, which sits in here, or my error vector. This is the squared error, and this inside here is the error vector. And I need to linearize it and compute the first derivative with respect to the parameters, which are again tx, ty, and my rotation component theta. So I have my Jacobian, my error vector over here derived with respect to tx, ty, t theta. The thing to note in here is that this expression over here is a 1D error function. So this is a two-dimensional vector. This is a two-dimensional vector, but we're computing the dot product of this two-dimensional vector. So this turns just into one single number. As a result of this, this Jacobian is not a 2x3 matrix as it was before. It's now 1x3 vector that we have in here, right? So we just have 3 columns that my Jacobian has here. And now what we need to do is we need to compute, again as before, the first derivative of this whole expression with respect to tx, ty, t theta. And what basically changes here, we had the expression we had before, but now I have the dot product with the normal vector. So we have basically need to multiply the terms that we had before with the x and y component of the normal vector over here. So basically the first two elements, here again, this is a linear expression. So this just gave basically a constant of 1. So as a result of this, if we compute then the dot product, we have here the components of the normal vector come into the game. And for the third component, we had this longer expression from the rotation matrix. And again, we have here parts of the normal vector that come into the game in order to compute here the Jacobian. And then we simply take that Jacobian and then proceed as before. So we are computing our H matrix, we are computing the right-hand side, iterate as before. So we start again with our example. We have our point-to-point correspondences. Here we are always showing the basically correspondency to the closest point, which then was used to compute where the normal was used in order to compute then the error function. And we again can minimize this error function and compute the alignment, which now takes the normal information for this alignment into account. And what we can see here, so you have to be a bit careful with this plot because the scale is a little bit different as compared to the plot we have seen before. But what we generally see, the error drops faster to a low value. So in this example here, after kind of 10 or let's say 11 iterations, we converged before, I think it had been 16. But again, the scale is a little bit different of the axis, so you can't compare those plots immediately or have to take care if you compare those plots. And so this is an example of the 2D point-to-plane metric now using the least squares approach for minimizing it. The problem of the point-to-plane, or one, let's say, problem issue of the point-to-plane metric is that it's not symmetric. So depending if you compute the error from seeing from one point or the other point gives you a different result because the normal information is different in one surface or point set compared to the other. So if we want to fix this and propose a symmetric point-to-plane metric, which takes which is symmetric independently if I'm using the normal vector from one cloud or the other cloud, that's what we may want to have. So just as a comparison, the point-to-point was just computing the difference between the points. The point-to-plane was taking basically one point and computing the normal information, using this normal information and taking this arrow vector, the same one over here, and projecting it on this normal vector. So this was basically the result that I was getting. But obviously, this would only be symmetric if I would have the same normal vector here for this point. It would have the same normal vector than this one, which typically is not the case. So if you, for example, have these points with different normal vectors, so this is the same normal vector, the one we used before, and now this is a different normal vector over here, then the question is, how can I define a metric which is symmetric, so can take both normal vectors into account? And a fairly simple approach, which has been proposed a few years, not many years back, actually quite recently, and very easy solution, is just average those normal vectors, just sum them up. So what we can do is we can compute the plane as the average of the two normals. So we compute a new vector n over here, normal vector, which is simply the sum of these two normal vectors that I had in here. And then I'm using exactly the same error function as I had before, but now multiplying it not with the normal vector in of this blue point over here, but basically this new normal vector, which is the sum of the other elements. So basically, it's an approach very similar to the point-to-plane metric, just taking one additional vector into account. So what I'm coming up with is a very similar formulation, except that I'm replacing the single normal vector with the sum of two normal vectors. So the only additional work that I need to do is to compute the normal vectors also in the other point cloud. Before I had to do it only for one point cloud, and now I need to also compute the normals for my second point cloud. But this is the only change that I need to do. And if I use this error function compared to the other error function, I'm typically getting a better result when aligning point sets. So this is an example. What you see here is the result that you obtain with the symmetric metric. This is centered point-to-plane. This is point-to-point metric. You basically have the error before the ICP iteration and then the error after the ICP iteration. So depending on the initial error you had, you're basically mapping it to the output error. And so what you can actually see, this plot is always lower than the point-to-plane metric, which is always lower than the point-to-point metric. So you can see you get actually better results for the alignments using this symmetric metric over here. So fairly easy, let's say, improvement that you can do, which is very easily implemented. The only thing that you need to do is to add a second vector over here, and this simple change leads to a better convergence speed, because you can quicker reduce the error, then potentially make better data associations, and then faster converge to the right solution. And also you can show that it increases the basin of conversion. So the more error you have in your initial alignment, still you get good data associations, and as a result of this, come up with a better solution. So aligning your point clouds correctly despite a larger initial error. So this symmetric metric over here is probably the thing you want to start with when you build your own ICP solution. The next thing that we can take into account in the context of the least squares approach is to do an outlier rejection. So in terms of least squares estimation, we often refer to this as robust least squares, where we don't take the residuals into account as they are, but we can downweigh residuals which are likely to belong to an outlier. And there's a standard approach which is available since a long time on reducing the impact of data association errors or outliers in our estimation techniques. And there's something which is often referred to as robust kernels or M-estimators. So what we are doing if we are computing or doing a standard least squares is we are basically have a quadratic error function, right? And so the further we go away on the x-axis, the larger the error gets quadratically. That is the relation to the Gaussian distribution, where we are basically computing the mean of the Gaussian distribution with this form. But the problem with this is that the probability of points with very large residuals is actually very small if I assume this Gaussian, and they basically drop to something close to zero until I'm whatever 3, 4, 5, 6 sigma away. It's basically zero afterwards, and this is not what happens in reality. There's a certain probability that we have strong outliers, typically because something happens in the scene that we haven't probably taken into account or modeled when designing our noise values or error functions. So what we can do in this robust estimation is to use a different kernel function, or using a different function instead of a quadratic function to which we squeeze our error vector. This can be just linear, so just the absolute value. This could be things like here in the around the actual error, we keep our quadratic form, but then at some point in time we turn it into a linear function, though that the growth is only linearly outside this area over here, which basically says close to the correct solution we are assuming our Gaussian noise, but further away we are kind of downweighing the impact of those points, not taking them quadratically into account but linear. So this is, for example, a Huber function or Huber kernel that is used, and you need to basically define your kernel function depending on your outlier distribution. And so, for example, these values give a smaller weight to points which are very far away. You can hear the impact even goes more or less constant. So this will basically not penalize an error larger if it's 2 or 10. Basically doesn't make a big difference anymore in this kernel. So depending on the error function, which tells you something about the assumption that you make about your outlier distribution. And there is, again, a large set of different kernels that you can actually use. There's a large family of different kernel functions, and you basically need to find the kernel function which best fits to your data. And how is this taken into account? So you basically squeeze your error vector through one of those robust kernels. And so as a result of this, your Jacobian will change. And you can actually turn this into a weight factor that you put into for every error term. So basically every error term gets an additional weight and basically downweighs those errors in the minimization. But again, the choice of this kernel function depends on the outliers that you're actually experiencing. Here's an example of different error functions. So this is a quadratic error function over here, and this is basically different forms of downweighing the impact of outliers. So this is basically the error term that you get the further you're away from your, in this case, from the 0 point, which is the minimum error configuration. And the shape of those kernels basically turn into weights. So the weight of 1, which is shown over here, corresponds to the quadratic term. And depending on the different kernel shape that I'm using, I'm basically reducing the weight the further I'm away from the zero error configuration. And what you can do is you can take into account these different kernel functions by not just selecting one of those kernel functions, but there's actually a family of distribution where you have this parameter alpha over here, which basically interpolates between those functions over here. So you can start with alpha equals to 2, you will get this quadratic form, and as you increase this value, you are basically moving down here and reducing the impact of outliers. And what you then can do is you can actually solve your least squares problem at the same point in time, optimizing your alpha parameter, so that you're basically adapting your robust kernels to the actual outlier situation that you have. And so this was an example I think I've also showed in the second part of the lecture. This is an example on the Kitty highway scene where you have a car driving over the highway, very little structure around, and then a second car comes and overtakes the actual car, and the overtaking car provides a lot of structure. So the ICP algorithm often hooks to this car and aligns the car against the other moving car, and this of course screws up the point cloud alignment and the motion estimation of the car quite substantially. And this happens if you use, for example, a Huber loss, but if you take this adaptive kernel into account, which estimates the shape of the outlier distribution for the current situation, then you can actually perform better. And this is an example, a video where you can see the car driving around and building a map of the environment. And so the different colors here are just kind of the different type of objects that we are seeing, so some semantic information. And we first can run this with a fixed kernel, and you can see a second car showing up here very soon in blue over here, and it's approaching the car. And as soon as it overtakes the actual car, this car will register its position against the moving car over here. And so it leads to a failure in the registration because the car basically hooks to the other car and localizes with respect to the other car. If you use this adaptive kernel approach, you see the car approaching over here, and then this alpha parameter will drop to very small values, which basically performs a very strong outlier rejection. And then this car doesn't hook onto the other moving car, and you're able to better deal with the outliers and not lead to a wrong alignment just because your outliers are very prominent. So in practice, what happens is you need to take into account your outliers if you want to build up robust registration techniques, and you need to do this properly in order to adapt to the situation. So there are two ways you can do this. On the one hand side, you can use some heuristics, so something that you know about your problem in order to reject outliers. If you know that only certain parts in your environment is potentially moving and other parts is static, you can actually exploit this information because you put background knowledge into your process. This can be seen as good because you're exploiting additional knowledge, you will get better results. But it can also be seen as bad because you're exploiting something which is problem specific, so your solution will not generalize well into other situations, always kind of the trade-off that you need to do. And there are different ways of using those heuristics that you can exploit, but the other thing is to use these more general methods like this kernel rejection techniques so that you can exploit the best of both worlds. So if you have some information about the environment, use it explicitly to identify what is a potential outlier, or at least not taking it into account in the initial registration steps, and then combine this with a robust kernel. In the easiest case, it could be whatever, a Huber kernel, but these adaptive kernels typically perform better because they can adjust themselves to the underlying outlier distribution, which is better for you. And you can also ask yourself, if you build up one of those systems, are there certain parts of the environment which I know they are static, so I can rely on them more than on others? You can ask yourselves, do I know something about my ego motion? Am I driving on a car? The car is not going to move sidewards, for example, at least not substantially. And these are all information that you can take into account in order to perform better. And this is something I also talked about in part 2 of the lecture. What you can also do is, if you build multiple of those techniques, let's say you take the point-to-point algorithm, you take the point-to-plane, you take the symmetric one. Maybe you have a strategy where you say, okay, let's take additional knowledge into account and estimate the pose. But maybe I also want to have a more general approach which also performs well in other situations. So you can actually build multiple registration techniques, or multiple, what we sometimes call sensor odometry estimation techniques, where you use sensor information in order to estimate odometry. What you then can do is you can actually combine multiple of them. So let's say this way, you have this vehicle moving through the environment and you have different odometry proposals. Let's say one taking robust kernels into account, one using point-to-point, one using point-to-plane, one using additional color information, one using semantics, whatever. You name it, you can generate different proposals. And so what you then can do is you can check how well is the result that this proposal estimates actually in line with the motion. And you can basically join up multiple estimation techniques and then do some, let's say, sanity checks, something you know about your vehicle, for example, to exploit to see which of those proposals are likely to be wrong and which are more likely to be correct, and then select a proper registration or odometry in every step in order to come up with a robust motion estimate. And it turns out that there's no best solution. So different algorithms which are chosen different times in the algorithm. You can see here, this is a generalized ICP, which is basically a combination of this point-to-point and point-to-plane registration technique. And point-to-point are the most commonly picked ones. Sometimes you want to use color information. So this is basically how often has one of those algorithms been picked in typical driving situations where it performed the best. And you can see there is no best solution. There are always situations where a certain algorithm performs better than others. And combining those different approaches and then deciding which is potentially the best alignment I can get in the current situation can be exploited if you really thrive for building robust estimation algorithms. So a few remarks from practice. You should always exploit your initial guess if you have an initial guess. So this is one of the recommendations. Never ignore an initial guess that you have. This initial guess will be valuable for you because it probably gives you a better data association in the first place, and then your registration algorithms will perform better. This could also be things like a constant velocity model. So if you don't have, let's say, an additional odometry source, you may take into account just repeating the movement that you have estimated before if you do an incremental estimation technique. Because very likely you're moving with a vehicle that is driving at a constant speed. It's not changing speed all the time. And this can be taken into account in order to come up with a better initial guess, just a constant velocity model, for example. As a general remark, the normal-based distance metrics typically perform better than the point-to-point alignment. There can be other situations, but from my experience is that those which use normals typically perform better. So, for example, this symmetric approach is one of the things would be my first starting point if I build up a standard registration technique, because it's sure to be better than point-to-plane, and point-to-plane was a standard for a long time. So that's probably a good start, is to start with this symmetric approach. As I said before, whenever you have information about your outliers, or also which part of the scene are likely to be not outliers, exploit this explicitly. So this is what I call informed outlier rejection. Apply it if it's possible. It will lead to better results if you can exploit specific properties of your scene, of your problem. But of course, you need to take into account that this may limit the applicability of your algorithm if you want to do a very general approach which works in all environments. And the adaptive kernels, we found them quite powerful in order to adapt the current situation to or adapt the robust kernel to the current outlier distribution, and then perform good results and not needing to commit on a specific kernel beforehand. So these are kind of some remarks that you could take into account when you build your own registration algorithms. There are a few more. So if you have this, what we call sensor odometry, so where you estimate the movement of a vehicle based on an ICP or ICP-like algorithm over time, you can do actually a couple of things. So first, if you have multiple sensors, take multiple sensors into account. Even if you, for example, have a laser scanner and a camera and you want to estimate using both sensing modalities, you can treat them independently and estimate transformation parameters just based on your camera. Even if it's just a single monocular camera, you can at least derive 5 degrees of freedom out of the 6 degrees of freedom from your camera. And typically cameras provide you with a really good orientation estimate. So you can take actually multiple sensors into account, either fusing them, using them jointly, or using one as a kind of sanity check for the other, and only if all of them agree, you say, okay, that's a good way to go. It's one example. Velocity constraints or other dynamic constraints. Your car won't accelerate from 0 kilometers per hour to 100 kilometers per hour within a second, or very unlikely it's going to do that. So exploit constraints because they allow you often to identify certain failure cases. And what the incremental registration does, it provides you incremental corrections. So you're always registering against the previous scans or the previous 5 scans or 10 scans, but typically not much more. So you're building basically a local map and always align against your local map. If you really want to get drift-free in the long run, you need at some point in time go to a SLAM algorithm and then probably perform some global optimization, some global least squares on aligning a trajectory. So also changing a trajectory in the past in order to close loops correctly and get globally a good estimate. So the incremental odometry only keeps you active for a while. The further you go, the more you may then want to turn it into a SLAM system. As a last remark, especially when SLAM comes into the game, from my experience, the uncertainties that you're estimating with an ICP-based approach are typically not that great. So typically, you tend to overestimate the accuracy of your alignment or the precision of your alignment with respect to what happens in reality. So I tend to not trust the uncertainties you get out of your scan alignment too well. Again, there are special techniques also recently being proposed that try to do better on that. But in general, I would be a bit careful with the uncertainties that you get from a scan matching estimation technique. But you can take them into account to some degree, but put it in use it with a grain of salt, and you can integrate it into SLAM algorithms. So this is an example of a LiDAR-based SLAM system that we have been built, or Jens Belay was the main contributor here, which uses ICP with a projective data association, basically matching the current laser scans against a circle-based map representation, again taking the normal information into account, using robust kernels so that you can then build maps of the environment. So these are all sequences of the KITTI data set, and building maps of the environment using this sensor data correct for loop closures so that you get a proper trajectory estimate out and map of the environment. So basically estimating where the sensor was and building a map of the environment at the same time. And that's what you can do is if you combine the point cloud registration techniques that we have discussed here with SLAM or global optimization techniques. And with this, I'm actually coming to the end of what we call the rigid registration, so where we have one rigid body transformation to transform one point cloud into another one. We can, however, go a step further. So there are different applications where autonomous systems or intelligent systems are faced with deformable objects. Like me as a human, I can deform, I can move my arms. And these are things that a mobile system or robot may need to take into account. So there are steps towards non-rigid registration. They actually have been around since quite a while. So already 20 years ago, people investigated into non-rigid registration of point clouds. For example, seeing which part has changed and may be able to deform some aspects over here. A lot of the work has been done here based on humans. So humans have a certain skeleton, a certain structure, and can we exploit the skeleton structure in order to perform a matching and knowing that my arms can only move in a certain way. And this, of course, information that we can exploit. We have been using the non-rigid registration also for other tasks, like dealing with growing plants. If you have 3D models of plants taken at different points in time, you may need to align or want to align those points or to track the growth of the plant, for example, over time. And you can do this by transforming one point cloud into another point cloud in a non-rigid way. And this is something where you need those least squares approaches as well. You typically have more complex cost functions into account, and sometimes even the least squares methods may not be the best choice. There are other approaches taking deformations differently into account and then using finite element methods, for example. That's something we're not going to cover here, but with the least squares approaches, you can actually go pretty far in here. And what typically happens if you will have additional cost terms in your optimization problem, for example, taking into account that you don't want to change the topology of your scene, at least not substantially, only to allow for small changes and different things like this. So this is an example how that could look like. So this is a point cloud of a plant at day 1, day 6, and day 10. So this is a tomato plant. And you see the point clouds, and you can imagine that it may be very tricky to align this point cloud with this point cloud to, for example, estimate how has the stem been growing, what's the change in the size of the leaves, things like this. But what you can do is you can actually try to do this, and again, a tricky way is how does the data association look like? And especially for these type of non-rigid registration techniques, you need to invest a lot of brain power into the data association between those points. And so this is, for example, 2 point clouds which have been just a day away, and you can see here is a small leaf is branching out here. So this here the plant only has 2 leaves, here there's 3 leaves. And if you want to do the registration, it's helpful to exploit additional information, like in this case, skeleton information that you have over here. So you can fit a skeleton into the stem and into the leaves and try to make the data association based on the skeleton, just exploiting how plants typically grow. And also saying, yes, there can be new branches coming out at some points. So that you then need to do the data association only based on those points on that skeleton. And again, you need to take into account that elements have been growing, and you may want to have different error functions being taken into account. For example, taking into account that transformations shouldn't change along the path. So what the approach is doing, basically every of those dots gets an own rigid body transformation, because everything can be moved, changed a little bit, or not even a rigid body transformation, it's even a fine transformation, because the thing can also grow. But what you don't want to do is that fine transformations of those points change dramatically. So you're going to want to perform some regularization of the change in the fine transformation along that way. And then you want to have certain regularization terms taken into account, so that you come up with a cost function which is more complex, but can realize this non-rigid registration, so that you can match one skeleton with another skeleton, even if it has grown, new leaves have appeared, so that you can then actually take your skeleton, match it against the other one, and then actually come to an alignment. Of course, the point cloud is still slightly different, because it has been grown, the leaf has been grown, but you can actually perform the alignment well for this skeleton, and then use the skeleton and transfer the information back to the overall point cloud, so that you then can even realize more complex alignments and then determine which parameters of the plant has changed. You can use this for phenotyping, for deriving phenotypic traits from this information, and then also, actually, if you do this in between all the time steps, track the development of the plant over time. So this is a small example of a video. So these are the points where you have actually taken a scan, and the red one is always an interpolation between those 2 clouds. So whenever it overlays with this one, you see, okay, this is the exact measurement, the point cloud, and then you can actually turn to interpolations and estimate how the plant will actually grow over time, and perform some visualization interpolating the plant growth, and then actually track phenotypic traits between those plants over time, although you hadn't had measurements at these positions. And those are things that you can do with non-rigid registration. Again, often people are using this in order to deal with humans. So a lot of the literature looks into humans and aligning clothes, which is non-rigidly moving, and taking this information into account. And so there's a whole set of more complex registration techniques than just the rigid body transformations that we have discussed here. I just want to show this as an outlook where you can go if you want to dive deeper and are interested in those techniques. There is a lot of literature out there for aligning humans or other non-rigid objects. With this, I'm coming to the end, and I want to point out a few resources that I found useful if you want to dive deeper. So the first thing is the Jupyter Notebook by Igor Bogoslavskyi, which provides you a very easy dive into an examples, everything done in Python, performing the simplest form of point-to-point registration using the SVD approach, then using the least squares approach, all done in 2D. So some of the examples that you have seen here actually stem from his notebook, and then also performing outlier rejection with a simple robust kernel. These are examples that you can see here with a few lines of code in Python. You can actually generate that. Of course, you can do better. You can take more heuristics into account, but I found this a very good starting point, both for learning, but also if you want to use this as a starting point for further projects. So highly recommended to look it up. Then there are also libraries out there like Open3D, one example, provides you with existing point-to-point or point-to-plane registration techniques. If you just want to use it as an out-of-the-box tool, you don't want to dive deeper, Open3D is at least one library you should look into. Maybe it fits your needs, and you can form different types of mapping and map building using scan registration techniques out there. If you want to look into further material, read papers, I have here a list of papers that I found useful, which cover certain parts that we have discussed here in the different lectures. This goes to very early works like from Arun and Bessel and McKay, proposing the ICP algorithm or this SVD-based alignment, over more recent techniques, overviews, efficient variants of the ICP, comparisons of ICP, which metric is better in which situation. So there's a large body of literature trying to come up with techniques supporting the ICP, better dealing with outliers, adding redundancy, going for global ICP methods. So there's a large body of literature that you may want to dive into, and then in the end maybe even use it to build up your SLAM system based on what you've seen here. And again, if you want to start with code, the Jupyter Notebook by Igor Bogoslavskyi, or there's also a simple ICP by Philip Iglira that is publicly available, which you have in, I think, Python, Julia, C++, MATLAB, Octave. So a lot of starting points to play around with to start with a simple ICP and then go deeper. And with this, I'm coming to the end. So this was a 3-part lecture on point cloud registration, looking into ICP and its friends, let's call it that way. And it's an important task in robot perception, in mapping, that you need to be able to align point clouds, either by shifting the sensor location and have the point clouds aligned, and sometimes even going further and optimizing the point cloud positions, or the point clouds itself, or the positions in the point cloud itself. ICP, or the iterative closest point algorithm, is the standard choice. So whenever you want to build a new system, you will always have to compare yourself against ICP and probably different variants of the ICP for performing incremental scan matching, for aligning point clouds. And what it basically does, it computes a translation and a rotation between point clouds or scans or surfaces, depending what your underlying structure is. And if you have a given data association, that's easy. If you don't have data association, then it can be tricky, and the data association determines your translation and rotation parameters. And the major problem is actually determining the correct data association. If you know your data association perfectly, it's easy. And getting the data association right, which includes finding out which points to trust, how does the alignment look like, which points are outliers, which to not take into account, which belong to moving objects. If you have all that solved, that's easy, but determining this is typically tricky. And what happens in practice is that you have an iterative approach, performing the data association, then the alignment, then again the data association, then the alignment, and so on and so forth. And there are several variants how you can do this, and in the most general form, you end up using a nonlinear least squares problem. And again, your initial guess is always helpful, especially if you go for the least squares approaches. You will not be able to get very good results without an initial guess unless you can make very strong assumptions about your theme, which then is similar to an initial guess. And what you often find if you look to more sophisticated algorithms is there will be a least squares approach probably being used. There's probably some point-to-plane metric or plane-based metric being used. There is some data association heuristics involved in maybe looking into which points are compatible to have a good starting point with, and then also some outlier rejections which are implemented in here. So this is kind of the standard ingredients that you find today in popular SLAM algorithms. And with this I'm coming to the end, and I hope you find this video useful. And if you want, there's also a 5-minute summary on the iterative closest point algorithm that I recorded within my 5 Minutes with Cyrill series. If this was all too long, 3 hours of ICP, you can just enjoy this 5 minutes. So thank you very much. So ICP stands for iterative closest point. It's a technique in order to align two point clouds with each other. So what means point cloud alignment? A point cloud is typically a set of points of 3D or in 2D. And what we want to do is we want to compute the transformation between two point clouds. And the goal is that through this transformation, points that are the same point in the real world actually lie on top of each other so that we can incrementally build a consistent model of the environment. And therefore, that's a key building block of most SLAM algorithms, for example, those that work based on laser rangefinders or RGBD cameras. So how does that work? Let's dive into an example and understand how this ICP algorithm works. It basically has 2 steps, a data association step and then a second step computing the transformation based on that data association. So the first step, let's say we want to align the blue and the red point cloud seen over here, and we do this using a simple nearest neighbor approach. That means we iterate over one point cloud and look for the closest point to these points in the second point cloud, and then make this alignment. And these are my correspondences, my data association that I have guessed based on this initial configuration. The second step takes this data association and tries to find the transformation so that those two point clouds are moved on top of each other, so to say, so that the distances of those corresponding points actually get minimized. And this is done using two steps. The first step computes the center of mass of those corresponding points and shifts the point clouds on top of each other. And the second step computes the optimal rotation using an SVD-based approach so that the points then are better aligned with each other. Why better and not perfect? Because our initial data association may not have been perfect. So what we do is we repeat this process, and based on the guess that we have right now, how the point clouds are aligned, we recompute our data associations and then recompute the alignment. And we do this over and over again. Data association, alignment, data association, alignment, data association, alignment, until we converge. And this is basically the vanilla ICP algorithm, the iterative closest point algorithm in its basic form. In practice, there are several variants out there how you can optimize the ICP algorithm. One prominent example is the point-to-plane metric. Here you assume that the points don't stem or are not distinct points in the environment, but they actually stem from a surface. They're basically randomly sampled through the scanner from a surface. And by making an alignment between the point cloud and a surface, we don't create an artificial point-to-point alignment, which may not exist in the real world. And this point-to-plane alignment typically, or point-to-plane metric typically gives you a better result of your ICP algorithm. But what it does, it requires that you leave this SVD-based approach and you have to go to a general least squares approach. And then you would most likely use the Gauss Newton method in order to minimize the error under this point-to-plane metric. But there are also several other variants out there, such as techniques using a projective ICP. That means you take the model that you have and project it, for example, into the range image that you created from your scanner and then try to find the alignment. You may also want to take into account robust kernels in your error minimization approach in order to better deal with outliers. So if you have outlier situations where some of the points are really wrongly aligned, then those outlier rejection techniques help you in order to weigh those points down and ignore them in your data association or reduce their impact when then computing the transformation. So there are several variants out there, and it depends a little bit on the problem that you are addressing, which of the variants you want to use, but a point-to-plane metric is probably today the standard for aligning point clouds, for example, those that stem from a laser range scanner. If you want to investigate the ICP algorithm further, I suggest visiting the Jupyter notebook that has been created by Igor Bogoslavskyi and that guides you through the SVD-based approach to the least squares approach, telling you how you can deal with outliers. And it's a very good starting point which you can grasp in a rather short amount of time how ICP works and providing you with a very simple Python implementation for this. So I hope that was useful and you get an idea how the key building block of most laser-based SLAM systems work. They are used in robotics, in autonomous cars in order to build consistent models of the environment whenever you have, for example, a 3D laser rangefinder mounted on your mobile platform. I hope that was useful and you learned something.